Okay, ladies and gentlemen, you are welcome. So in the present video, we are going to look at current electricity with work examples. And please don't forget to subscribe and join to my YouTube community. So what is a current electricity? A current electricity, it involves the flow of electric charges through a conductor. So a current electricity is one of the area of electrostatic physics or electricity and magnetism physics where we are talking about how the electrical charges flow through a conductor. So that is what we call a current electricity. The flow of electrical charges through a conductor is what we call current electricity. And this current electricity is very important for powering devices and electrical system in daily life. So almost in daily life, almost all the activities that we are doing, including the devices we are using, like our phones, the computer system, are all powered by current electricity. So therefore, understanding its principles, it helps in designing and troubleshooting electrical circuits. So if you have electrical circuits, so by understanding the concept of electricity, it will actually help in designing and troubleshooting an electricity within a particular devices. And as we can see, this is how we have the circuit. This is an electric circuit. And as we can see, this is how electrical current, or this is how electrons are following through the conductor. So the next thing that we are going to look at is current. Current and its units. What is a current? A current is the rate at which charge flow through a conductor. So the rate of flow of charges through a conductor is what you call an electric current. And this electric current is measured in amperes. It means that the SI unit for electrical current is ampere, which is represented by capital letter E. And very importantly, 1 ampere is equal to 1 coulomb of charge passing a point per second. So that is why an electrical current has a formula of I, as we can see. I is equal to Q all over T. The Q means the charge in coulomb, that is the quantity of electricity, and the unit for this Q is coulomb. And then this is time, that is the time taken for the electrical current or electrical charges to pass through a conductor, and it is measured in second. So you can see that current, that is I, current is represented with capital letter I. It has a unit of, we can say, coulomb per second or ampere. So that is an electrical current. That is the rate of flow of electrical charge along a conductor. That is what we call electric current. The unit is ampere and the formula is Q all over T. So then the next thing is types of electric current. So basically we have two types of electric current. So we have two types of electric current. We have direct current and we have an alternating current. DC means direct current. It means it is actually a flow of electric current in a single direction, typically from batteries. So a direct current, it means it is a current flows in only one direction. So that is what you call a DC, that is called a direct current. Then alternating current, it usually changes direction periodically and is used in household power supplies. So these are the two types of electric current. We have DC, direct current, and we have alternating current. So alternating current, it usually reverses direction in equal intervals of times. So that is what you call alternating current. So it changes direction periodically, and it mostly this alternating current that we use in our house or in our household power supply. So you can see only in one direction. So it can reverse the direction in equal intervals of time. So these are the two types of electric current. So then the next thing that we are going to look at is Ohm's law. So what is Ohm's law? Ohm's law states that the current flowing through a resistor is directly proportional to the voltage. So it means that the current, which is I, or the voltage, is directly proportional to I. So there is a direct relationship between a voltage and a current. And of course, remember, whenever there is a proportionality, we introduce constant. So therefore, this implies that we have V is equal to the constant here is I. So we have IR. The R here is resistance. So this laws, it helps in calculating current, voltage, or resistance in a circuit. So if you want to calculate the amount of a current or a voltage or a resistance of a circuit, you can use this Ohm's law, which is V is equal to IR. The V is voltage, I is current, and then the R is resistance. And very importantly, the voltage V is measured, or it has a unit of volt, the current has a unit of amperes, and then the R, resistance, has a unit of ohms. So now let's look at some example. Now, calculate an electric current. So here we are going to calculate an electric current, and we are given a voltage of 12 volts and a resistance of 6 volts. So therefore, to calculate current here, to calculate the current as unknown, of course, we have V is equal to IR. So we can make I subject of the formula by dividing both sides by R. So this will now cancel this. So we now have I is equal to V all over R, and then the V given here is 12 divided by R is 6. So therefore we have 2 ampere. So that's why here we have 2 ampere as the answer. So now the next thing that we are going to look at is resistance and its factors. So what is a resistance? So the resistance is a measure of how much a material opposes the flow of a current. So the rate of the a resistance is a measure that used to opposes the rate of flow of electricity in a conductor. So it means that the higher the resistance, the lower the current that will follow through the conductor. So that is what I want us to understand. So resistance is like a measure of how much a material will resist or will oppose the flow of a current. So we have a factors that affecting this resistance. So the factors that affect resistance, we have nature of the material, length, cross-sectional area, and temperature. So these are materials that affect the resistance, cross-sectional area, and a temperature. I think we have even a formula that can give us this relationship. There's a formula that can give this relationship. There is a formula that says R, that is resistance, is equal to rho E all over length. It means that the higher the resistance, the lower the length. And the lower the length, the higher the resistance. So it's inverse relationship. And then the area, that is the cross-sectional area. So it means that the higher the resistance, the higher the area. And the higher the area, the higher the resistance. So it's a direct relationship. So metals typically have lower resistance, while insulators have high resistance. So because metals, they are materials that allow electricity to pass through them. So that is because they have lower resistance, that is why electric currents can pass through them. And insulators, they are materials that doesn't allow electricity to pass through them. And this is because they have higher resistance. That is the reason. So now, another example, worked example, resistance, calculation of resistance. So here we have a voltage of 9 volt, and then we have a current of 3 ampere. So we are to find resistance. So of course, within the same formula, V is equal to IR. So what we are going to calculate here is resistance. So we can make R subject of the formula. So this will cancel this. Then we now have R is equal to V all over I. And then the V is 9. The I is 3. So this will now give us 3 ohms. So that's why here we have 3 ohms. Then the next thing is, of course, series and parallel circuit. So we have resistance in series and also in parallel. So in series circuits, components are connected end to end and current is the same through all. So in the case of resistance in circuits, the circuits or the component are connected end to end and the current through the circuit remain the same. So as we can see here, the series arrangement, as we can see here, here is the series arrangement where we have voltage is equal to, the voltage in is equal to V1 plus V2 plus V3. And then for current in series is equal to I1 is equal to I2 and is equal to I3. So that is why the equivalent resistance in series is equal to R1 plus R2 plus R3. So to calculate the resistance in series, so we are going to use the resistance equivalent is equal to this formula, that is R1 plus R2 plus R3. And then for the resistance in parallel, we are going to use this, that is 1 all over resistance equivalent is equal to 1 all over R1 plus 1 all over R2 plus 1 all over R3. So if one component burns, current becomes inactive. And of course, if one component burns, then the current stops only through that branch, rest part works. So this is actually the resistance in series and in parallel, and we have their different formula that we can use in calculating resistance in series and in parallel. So now work example. So given that we have R1 is equal to 4 ohm, and then R2 is equal to 6 ohm. So we are now to find the resistance total in parallel. So to do that, we are going to use, of course, 1 all over R effective or equivalent is equal to 1 all over R1 plus 1 all over R2. And this will give us 1 all over 4 plus 1 all over 6. So therefore, from here, we can now take LCM. So which at the end, we are now going to arrive at this. I hope you understand. And you also have, if you can see also clearly, ladies and gentlemen, this is how to calculate resistance in parallel. So we can also look at another example. Okay, let's actually in summary and applications. Current electricity is fundamental to modern technology and electrical engineering. So understanding Ohm's law and circuit configuration is crucial for designing safe circuits. Practical applications include household wiring, electrical devices, or electronic devices and power distribution system. So ladies and gentlemen, this is actually a basic introduction to current electricity. Thank you very much and see you next in my next video.